Deep beneath your feet, right now, at the boundary between Earth's molten core and its solid mantle, lie two mysterious, continent-sized blobs of rock. For decades, they have been one of geology's greatest puzzles. But a groundbreaking new theory suggests these structures aren't from Earth at all. They might just be the buried remains of an ancient, long-lost planet that collided with ours billions of years ago. A collision that created our moon. This is the story of how we found the ghost of a planet hidden inside our own world, a discovery that is rewriting the very history of Earth. Our first glimpse of these strange structures came in the 1980s with the rise of a revolutionary technique called seismic tomography. It works a bit like a medical CT scan for the planet. When an earthquake happens, it sends waves of energy vibrating through the Earth's interior. By setting up networks of seismometers around the globe, scientists can track how these waves travel. The speed of the waves changes depending on the temperature and composition of the material they pass through. By analyzing millions of these wave paths from thousands of earthquakes, geophysicists can build a 3D map of the planet's interior. What these maps revealed was shocking. They showed two vast regions in the lowest part of the mantle, one deep beneath the African continent, the other under the Pacific Ocean, where a specific type of seismic wave, called a shear wave or S-wave, travels significantly slower than in the surrounding mantle. These S-waves, which move rock particles from side to side, are particularly sensitive to the physical properties of the material. A slowdown meant something was very different down there. And these weren't small anomalies. The African and Pacific blobs are immense. Each one is about twice the size of the moon. They extend for thousands of kilometers and rise up to 1,000 kilometers from the core mantle boundary. Scientists gave them the appropriately technical name, Large Low-Shear-Velocity Provinces, or LLSVPs for short. The immediate thought was, well, maybe they're just hotter. Seismic waves do slow down in hotter, less dense rock. But as our imaging technology improved and the data became clearer, that simple explanation didn't quite fit. The blobs have surprisingly sharp, distinct edges. A simple hotspot would be expected to have blurry boundaries, gradually blending with its surroundings. These were different. The sharp edges suggested they weren't just hotter, but also chemically distinct from the rest of the mantle. They were what geologists now call thermochemical piles. But that just deepened the mystery. If they're made of a different chemical substance, where did these two continent-sized piles of alien rock come from? The answer, it turns out, may not be found deep in the Earth, but far out in space, with the origin of our moon. For decades, the leading explanation for how we got our moon has been the giant impact hypothesis. The theory goes like this. About 4.5 billion years ago, when the solar system was a chaotic construction zone of colliding protoplanets, a Mars-sized body slammed into the very young proto-Earth. Scientists named this impacting planet Theia, fittingly after the Greek Titan who was the mother of Selene, the goddess of the moon. The collision was an event of almost unimaginable violence. It would have melted Earth's entire surface, turning it into a global magma ocean, and blasted a colossal cloud of vaporized rock and debris into orbit. Over a relatively short period, geologically speaking, this ring of debris clumped together under its own gravity to form the moon. This single, elegant hypothesis explains a lot, like why the moon has such a small iron core compared to Earth, and why the isotopic composition of rocks brought back by the Apollo astronauts is so remarkably similar to Earth's rocks. But it always left one nagging question unanswered. If a Mars-sized planet hit us, where is the rest of it? Some of it made the moon, some was surely ejected into space, but computer simulations of the impact consistently suggested that a huge chunk of Theia's denser, iron-rich mantle should have been absorbed and swallowed by Earth. For decades, we couldn't find any definitive trace of this alien material, until now. This is where two great scientific mysteries, the strange blobs in the mantle and the missing pieces of Theia, dramatically converge. In a brilliant stroke of insight, researchers began to consider a radical idea. What if the LLSVPs are the long-lost remnants of Theia? This hypothesis, that we have an alien planet buried in our own, has recently gained incredible traction thanks to a flood of new evidence from different scientific fields. At the forefront of this research is a team at the California Institute of Technology, or Caltech, led by geophysicist Qian Yuan. He and his colleagues conducted some of the most sophisticated computer simulations ever performed to model the giant impact. These aren't simple animations. They are complex calculations based on the fundamental laws of physics, factoring in the chemical compositions, temperatures, and pressures of the two colliding worlds. They specifically tested what would happen if Theia's mantle was denser than early Earth's mantle, a very real possibility, since planets forming in different parts of the early solar system would have had different chemical makeups. The results of these simulations were stunning. They showed that if Theia's mantle was indeed just a few percent denser than Earth's, the impact wouldn't have just mixed everything together like a blender. Instead, the simulations showed that massive, coherent chunks of Theia's denser mantle could have punched through Earth's molten upper layers, sinking like planetary-scale cannonballs through the magma ocean. They would have eventually settled on top of the more solid lower mantle, right at the boundary with the core. Then, over the vast expanse of geological time, the slow, churning motion of Earth's mantle, a process known as convection, would have acted like a cosmic shepherd, sweeping these scattered fragments together into two large piles. The size, shape, and location of these simulated piles were a remarkable match for the LLSVPs we actually observe with seismic waves today. Crucially, the models showed that their higher density would make them gravitationally stable, allowing them to survive for 4.5 billion years without getting mixed in and diluted by the surrounding mantle. But computer models, no matter how good, need to be backed by physical evidence. And some of the most compelling evidence comes from the very place Theia helped create, the Moon. For years, scientists were deeply puzzled by how similar moon rocks were to Earth rocks in their isotopic composition. Isotopes are versions of an element with slightly different masses, and their ratios act as a unique fingerprint of where that material came from. If the Moon is mostly made of Theia, should it have a different isotopic fingerprint than Earth? The Theia remnant theory offers a neat solution. If Theia's densest, iron-rich parts sank deep into Earth's mantle to become the LLSVPs, then the material that was blasted into orbit to form the Moon would have been a well-mixed cocktail of both planets' upper, lighter mantles, which would naturally share a more similar isotopic signature. And as our analytical techniques get better, we're finding more clues. More recent, high-precision analyses of the Apollo samples have found subtle but crucial differences that challenge the perfect mixing idea. For example, some moon rocks have been found to contain a different ratio of sulfur isotopes compared to Earth rocks. These small variations could be the faint chemical echo of Theia's original, alien composition, proving the mixing wasn't perfect. This is the smoking gun suggesting a part of Theia is still unaccounted for, and the LLSVPs are the prime suspect for where it's hiding. Further evidence for ancient, unmixed material inside our planet comes from a completely different direction. Studies of ancient rocks from Greenland and Canada, as well as lavas from volcanic hotspots like Hawaii, show a deficit in an isotope called potassium-40. This isotopic signature predates the giant impact, suggesting that not only are Theia's remnants down there, but possibly even some pristine chunks of the original proto-Earth's mantle survived the cataclysm relatively unscathed. The deep mantle is a museum of our planet's earliest history. If these blobs are Theia, studying them is like performing an autopsy on a planet that died billions of years ago. We can start to piece together what this lost world was like. Their high density, as inferred from seismic data and required by the simulation models, strongly suggests Theia's mantle was richer in iron than Earth's. This gives us clues about where in the primordial solar system it might have been born. One idea is that it formed in a stable gravitational spot in Earth's own orbit, a so-called Lagrange point, either trailing or leading us around the Sun. But another, more exciting possibility is that Theia was an immigrant from the outer solar system that spiraled inwards. This could explain a different composition, and it has huge implications. An outer system Theia might have been rich in water and other volatile compounds. The collision, then, wouldn't just have created the Moon. It might have been the event that delivered a significant portion of the water that now fills our oceans. The very cataclysm that almost destroyed our nascent planet may have also delivered a key ingredient for life. Now, as compelling as this theory is, science thrives on debate, and it's not a closed case. There are alternative ideas. One of the leading ones is that the LLSVPs are simply giant graveyards for oceanic crust. The process of plate tectonics, which drives our continents, involves creating new crust at mid-ocean ridges and destroying old crust at subduction zones where one plate slides beneath another. This theory suggests that over billions of years, immense amounts of this dense, subducted oceanic crust have sunk all the way to the core mantle boundary and piled up, forming the LLSVPs. It's a plausible idea that relies on a known, ongoing geological process, but many scientists still debate whether subduction alone can account for the sheer, mind-boggling volume of the blobs. Another possibility is that they are primordial heterogeneities, relics from the very earliest stages of Earth's formation, even before Theia. When Earth was a molten ball of magma, the heaviest materials would have sunk towards the core in a process called differentiation. The LLSVPs could be pools of this early, dense material that simply never fully mixed with the rest of the mantle. The scientific community is actively working to design experiments and observations that can finally distinguish between these competing hypotheses. But let's assume for a moment that these are Theia's remains. Their presence isn't just a historical curiosity. They are actively shaping our planet today. The Earth's mantle is constantly churning in a slow-motion boil, a process called convection, which is the engine driving plate tectonics. The dense, stable LLSVPs are thought to act like giant, immovable anchors in this flow, organizing the circulation patterns of the entire mantle. More dramatically, they seem to be the source of Earth's major volcanic hotspots and massive volcanic events, called Large Igneous Provinces, or LIPs. The intense heat flowing out of the Earth's metallic core heats the bases of these dense Theia remnants. This heat then conducts into the surrounding, normal mantle rock, causing it to become buoyant and rise as massive plumes of hot material. When these plumes reach the surface, they can burn through the tectonic plates, creating massive volcanic chains like the Hawaiian Islands or the supervolcano under Yellowstone. Intriguingly, many of the world's major hotspots and the locations of past lips, which are associated with some of Earth's largest mass extinctions, are located directly above the margins of the two LLSVPs. In a very real way, the ghost of Theia could be the ultimate source of some of the most powerful and destructive geological forces on Earth. This influence may even extend to the grand billion-year cycle of supercontinents. The massive upwellings from the LLSVPs might have provided the power needed to crack apart past supercontinents like Pangaea, while the downwelling currents around them might have guided where continents would later collide and reassemble. The geography of our world, for billions of years, may have been choreographed by these planetary fragments. This remarkable story of discovery is also a human story, driven by the curiosity and collaboration of scientists. The recent popularization of the Theia remnant hypothesis is largely credited to the work of Qian Yuan at Caltech. He describes having a eureka moment during a seminar where the question of Theia's missing remnants was raised, sparking the line of inquiry that led to his groundbreaking simulations. But science is a team sport. His work was in close collaboration with experts like Paul Asimov, a geochemist who studies how minerals behave under the extreme pressures of the deep earth, and Michael Gurnis, a geophysicist who directs the Caltech Seismological Lab and is a leader in modeling the long-term dynamics of the mantle. It's this combination of different expertise, seismology, geochemistry, and computational modeling that allows scientists to piece together such a complex puzzle. This discovery opens a whole new frontier in deep Earth exploration. The next major step will be to search for more direct, smoking gun evidence. Researchers are eager to analyze more lunar rocks, and more importantly, rocks from those volcanic hotspots on Earth that are believed to be sourced from the edges of the LLSVPs. They'll be hunting for unique isotopic signatures that could be definitively linked to an extraterrestrial origin, the chemical fingerprint of Theia. At the same time, seismologists are working on new techniques to create even higher resolution images of the LLSVPs, which could reveal details about their internal structure and their boundaries that will help prove or disprove the theory. The implications are simply profound. This discovery is rewriting the story of our planet's formation. It suggests that Earth isn't a single pristine world, but a geological chimera, a composite body with the heart of another planet still preserved deep within. It provides a tangible link to the violent, chaotic birth of our solar system. The work to confirm this theory is just beginning, but it's a powerful reminder that even after centuries of study, our own planet still holds secrets we are only just beginning to comprehend. We live on a world that was forged in a cosmic collision, and the echoes of that ancient impact are still shaping our world from deep beneath our very feet.